To this point, we've seen the importance of Newton's laws in understanding forces. We saw that using forces we could figure out how things got their acceleration and ultimately how their velocities changed. We also saw how forces were important for the work-energy theorem. Here, we're going to continue seeing the importance of forces, but in a different context. And this is in the context of momentum. Surely just about everybody has played a game of soccer before, or at least has seen a game of soccer being played. When the ball is stationary, a player kicks the ball, and then it begins to move. And so what we can say is that the foot is going to be imparting some force on the ball, which is actually causing it to start moving. One way we can describe how the ball starts to move is by considering a concept called impulse. So impulse is described or defined to be the force applied to some object times the amount of time over which that force occurs. We can also frame this in a slightly different way, and this is how we're going to talk about momentum. And we can say that the impulse, by definition, is going to be equal to the change in momentum, and the momentum is going to be the mass times velocity. So in a very conceptual, colloquial way, this definition of momentum seems to make sense. So the more mass something has, and if I have two objects and they're moving at the same velocity, but one has more mass, that has more momentum. And likewise, if I have two objects with the same mass and one's moving faster, then that one also clearly has more momentum. Now let's go back to our soccer ball example so we can describe this in terms of impulse. So what's happening here is the foot is going to be applying some force to the ball over some small amount of time, and that's actually what's changing the momentum of the ball. So when we talk about impulse and changes in momentum that can be imparted due to some force acting on an object, it's tempting to think about the forces that act between the two objects. So in the case of the soccer ball and our foot's acting some force on the ball, and that ball is in turn acting a force back on our foot. We're already familiar with the way that we describe these situations because we apply what's called Newton's third law. So in this case, when we consider the force our foot exerts on the ball and the force the ball exerts on our foot, we can say that these are going to be equal and opposite. Now, something that's useful to do is to consider what's called the system to contain both the ball and our foot. And if we do that, we end up finding that these internal forces, because they're equal and opposite, are going to cancel. If there are no external forces acting on this total system, this is what we say is an example of when momentum is conserved. So now that we've conceptually talked about conservation of momentum, we'd really like to put some equations to it so we can derive it more formally. So to begin with, what we can do is we can write down our definition for the impulse. That is that the impulse, which is going to be the change in momentum, is equal to the force times the change in time. Okay. Now when we look at this equation and we see that the change in momentum is equal to the force times the change in time, this force is really the external force, or the force that's external to the system. So if there are no external forces acting on this, what we can say is that the right term here is going to be 0. Now, if we look at this and expand our change in momentum is really the difference between the final momentum, so this is going to be Pf, and the initial momentum, so this is going to be Pi, and this is going to be equal to 0. We can rearrange this to say that Pf is going to be equal to Pi, but we also want to take into consideration that when we're conserving momentum, many times it's for more than one object. And so what we say is the sum of all of the final momentum is equal to the sum of all of the initial momentum. And this is our general statement of conservation of momentum. Now, looking at this equation, it kind of harkens back to another conservation that we had, and that was the conservation of energy. So if energy was conserved, we would say that EF is going to be equal to EI. Okay? So when we talk about situations where momentum is conserved, there are typically two types of situations that we're looking at. And these are different types of collisions. First, we have the elastic collision and the inelastic collision. So in the case of an elastic collision, the two objects are going to bounce when they hit each other. And we can say in that case that momentum is conserved, but also energy is conserved. In the case of the inelastic collision, the two objects are going to hit and stick and move off together. In this case, only momentum is conserved because there's some non-conservative force required to make the objects stick together. So let's first look at what happens in a one-dimensional elastic collision. So in this case, we could consider two objects, object 1 and object 2. So we'll have some object 1 with mass m1 that's going to be moving towards some object 2, we can say, with mass 2. So the first thing that we want to do here is to kind of draw what the initial and the final states are going to look like. So we can say this object 1 is going to move with some velocity, we'll say v1 initial, towards this object 2. And after they hit, let's assume that this object 1 has a mass that's less than object 2. When they hit, that's going to mean that this first object is going to bounce off of this and go to the left, so opposite direction it's originally going. And this object 2 is going to start moving off to the right. So we can label the velocities that we have here as v1f, and we can call this one v2f. Okay. So we have our initial state and our final state. It's also good to draw some coordinate system, and so we'll say that this is going to be the plus x direction. Okay. Now what we'd like to do is to write down some equations for our conservation of momentum. In general, what we can say is that the sum of the momentum initial is going to be equal to the sum of the momentum final. And note that this is some vector. Now in this case, this is only one-dimensional, and so this is going to reduce to the sum of the momentum in the x direction initially. And this is going to be equal to the sum of the momentum in the x direction in the final state. Okay. Now let's ask ourselves, what is the sum of the momentum in the initial state? Well, in the initial state, only object 1 is moving. Object 2 has no velocity, and so what we can say is that the sum of the initial momentum is going to be equal to m1 times v sub I1, and the sum of the momentum in the final state. Now, this has both objects moving, but we need to be careful because we define this x direction here, and this one's going to be moving to the left, which means it's going to have negative momentum relative to the coordinate system we've defined here. So the sum of the momentum in the final state is going to be minus m1 v1f plus m2 v2f. Now, to put this all together to form an equation, we just equate the top line to the bottom line, and so then we can say that m1 v I1 is equal to minus m1 v1f plus m2 v2f. Okay? So because this is an elastic collision, we have this equation for our conservation of momentum. But energy is also conserved, and so what we can do is we can write the kinetic energy of all of these objects and say that the initial kinetic energy, or the sum of the initial kinetic energy, is going to be equal to the sum of the final kinetic energy. So when we do this, we can say that the kinetic energy in the initial state is going to be 1/2 mvi1 squared. The sum of the momentum in the final state is going to be 1/2 mv1f squared plus 1/2 m, and this is m1. This one is also an m1. This is an m2 v2f squared. Okay, and so now we have two equations that we could get in this situation. Now, we could apply some more specifics to this, and so we could ask, well, we might want to know what the velocity is of this object after the collision if we know all of the masses and the velocities, but those are details that you could fill in for a specific problem. So now that we've treated the elastic case, we'd like to treat the inelastic case. So remember, in the case of the elastic collision, the object hits the other object and it bounces. In the inelastic case, kind of the opposite happens. They hit each other and they stick and move off. So let's consider an example here where, again, we're going to have some object mass m1, some object mass m2, where the object with mass m1 is going to be moving to the right with some initial velocity. We can say this is v1f, or sorry, we'll call this one some v1i. And then this is going to hit the object m2. So we have our drawing for our initial state. Let's also draw what the final state looks like. So for the inelastic collision, these two are going to stick together. So we can say that they're kind of like one blob here. So this is going to be the mass m1, this is the mass m2, and now they're going to move off with some final velocity. We can call this some v f. Okay. So first thing we should do here is write down our general equation for conservation of momentum, and we remember that that's going to be the sum of the initial momentum is going to be equal to the sum of the final momentum. And because this is one-dimensional, this is only going to have x components, and while we're at it, we should define what we're calling the positive x direction. So this equation that's written generally can be written as the sum of the momentum in the x direction initial is equal to the sum of the momentum in the x direction final. So then we just need to look at our initial and our final cases to evaluate what this equation says. So in the initial case, only the mass m1 is going to be moving. The mass m2 is going to be stationary, and so this is going to be m1 v1I. And now these two masses are sticking together in the final state, and they're moving with the same velocity. So what we can say is that this composite mass has a total mass of m1 plus m2, and then this is going to be multiplied by the final velocity of the system. So this is going to be vf. Now, again, we did this kind of in general, and so there are several things that we could ask here. So for instance, if I tell you what the initial velocity is, what the masses are, we could find what the final velocity is going to be. So in this video, we began by talking about impulse and how that can relate force to momentum. And then we talked about the different types of collisions that we can have in conservation of momentum. In the next video, Professor Shepard's going to be talking about how we can apply the rules and the concepts that we've learned in this video to some example problems. Thanks for watching.